Hello everyone, I welcome you all to this lecture. In this lecture, we are going to discuss a new scheduling algorithm which falls under the category of non-preemptive scheduling. Name I have already written on the screen. So that is highest response ratio next. It is also called as highest response ratio first scheduling, right? So let's discuss it. To apply this particular scheduling, you need to be aware about what is the meaning of response ratio. So response ratio you consider like at whatever the moment we try to decide out of n number of processes those are residing in ready queue which will be scheduled next. For that we calculate two things. One thing is the current waiting of the particular process in ready queue. That means from how much duration of time a process is waiting to get the CPU control plus the required CPU cycle. So I would say CPU burst or burst time. Let's say I'm writing burst time. Okay, and divided by burst time. So this is considered as response ratio. So whenever we schedule a process in this particular scheduling algorithm, although this is a non-preemptive scheduling, non-preemptive, so I'm considering non-preemptive case. Okay. When we try to schedule, or scheduler will take a decision, it will calculate this thing, and whichever the process will have the highest response ratio, that will be scheduled first. So let's take an example and quickly solve it. Consider there is this particular data is given. So let's draw the Gantt chart for this particular data based on the highest response ratio next scheduling algorithm. So this is 0 moment, and according to the arrival time at 0 moment only one process has been arrived, that is P1. So there is no confusion at the scheduler end, only P1 will be scheduled here at 0 moment. And if you are considering this is non-preemptive scheduling, so P1 will execute till 3 unit of time. So let's say this is 3 if you consider, then it will keep on executing till this particular moment. Okay, so let's say I'm assuming this is 3. Now at 3, if you look at the ready queue, process 2 has been arrived. In this data I have given you one extra parameter like priority. Priority may be given or may not be given, because we are giving the preference based on the response ratio. Okay, but priority we may consider when two processes at any given point of time is having same response ratio. So sometimes there is a conflict in case of response ratio. In that case, either we can go for process ID wise, or if priority is given, then we resolve the conflict by considering the priority. Okay. So let's say at this particular moment in ready queue, there is only one process, that is P2. So we will schedule P2 here. There is no confusion because only one process, remaining P3, P4, P5 has not arrived. So because they are not in ready queue, we cannot schedule, or scheduler cannot schedule them. So now P2 will execute, and P2 requesting 6 cycles. So from 3 to 9 you consider, let's say you consider this is 9. So this P2 will execute, right? Now at 9, if you look at the ready queue, P3, P4 and P5 has arrived already in the ready queue. So now we need to calculate the response ratio because there are more than one process in the ready queue. So if you calculate the response ratio, I am saying RR for process 3. Response ratio for process 3 is the current waiting time. So I am saying waiting time plus the burst time. So what is the current waiting time? Current waiting time of process 3, if you find out at moment 9, process 3 was arrived at 4 and right now it is 9, so it is waiting from 4 till 9, so waiting time will be 5. Okay, plus burst time it is already given, 3 is requesting 4 cycles, so it is 4 divided by burst time, that is 4, so it will give us 5 plus 4 divided by 4, so that is 9 divided by 4, and 9 divided by 4 will give us 4 2s are 8 and 1 by 4 will give us 25. Okay, so 2.25 will be the response ratio for 3. If we calculate the response ratio for process 4, process 4 at 9 we are calculating actually, so process 4 waiting at 9, process 4 is waiting from 6 till 9, so it is 9 minus 6, that is 3 unit of time, and it is requesting 5 cycles, so it is 5 divided by 5, and it is 8 divided by 5, and it will give us 1.6. Now if we calculate the response ratio, let's say here I am calculating response ratio for process, let's say 5 at moment 9. So when we calculate, this was arrived at 8 and we are deciding at 9, so 9 minus 8, waiting time or current waiting for process 5 is 1, plus required CPU cycles are 2 divided by 2, so 3 divided by 2 we will get 1.5. So here at moment 9 the highest response ratio is of process 3, so P3 will be scheduled here. Now when the P3 will be scheduled, because this is non-preemptive, P3 will consume 4 cycles, so it will finish somewhere here, let's say it is 13, right? So P3 has been finished, P2 has been finished, P1 has been finished. Now P4 and P5 are left. So at 13 we need to again calculate the response ratio for the remaining processes, and then we can decide which will be scheduled. So if you calculate response ratio for process 4 at 13, so you are at 13 and it was arrived at 6, plus required CPU cycle 5 divided by 5. So it is 13 minus 6, that means 7 plus 5 divided by 5, and it will give us 12 by 5, and it is 2.4. Now the response ratio for process 5, if we calculate, it is, we are calculating at moment 13, so 13 minus, it was arrived at 8, plus requested burst time is 2 divided by 2 only, so it will give us 5 plus 2, 5 plus 2, that is 7 divided by 2, so that is 3.5. That means it is having highest response ratio, so 5 will be scheduled, P5 will be scheduled here. So P5 will consume two cycles, so it will execute, let's say here it is 15, so P5 will execute and then remaining only 1, so this is finished. Now P4 will be scheduled. So when the P4 will be scheduled, it is requesting for 5 cycles, so let's say it will complete here, so it will finish by 20. Okay, right? So if you want to calculate the waiting time, you can calculate waiting time for process 1. Process 1 would arrive 0 and executed at 0, so it is 0. Waiting time for process 2, it was executing from 3, arrived at 2, so it will be waiting time is 1. Waiting time for process 3, 3 was start executing at 9 and 3 was arrived at 4, so it is 5. Now waiting time for process 4 start executing at 15 minus process 4 were arrived at 6, so it is 9. Then waiting time for process, let's say 5 start executing at 13 minus 5 was arrived at 8, so it is 5. Now if you calculate the average waiting time for the system, it is 0 plus 1 plus 5 plus 9 plus 5 divided by 5 processes are there, so it will give us 6 plus 5 11 plus 9 20 divided by 5, it will give us 4. Okay, so I hope with this example you must be having clear idea how to apply the HRRN algorithm, highest response ratio next algorithm. So thank you everyone for this lecture. I'm closing the session. See you in the next class.